So welcome back to the DSS session. So for some of you that have been coming back a few times, this is our third talk for this term. So I'm Professor Bouriba, and this is the Distinguished Seminar Series that is sponsored by the CC May Funds and the Civil and Environmental Engineering Department. So we had a few talks already on fluids this term, and we're going to have the next few talks are going to be concerned to different fields, one in actual healthcare, and the last one will be actually on solids and architecture. And so stay tuned and come back. But for those that are here for the fluid part, so today's speaker is Professor Cook, so Pamela Cook, who is the Unidel Professor of Mathematical Sciences at the University of Delaware. She completed her PhD at Cornell University, received a NATO postdoctoral fellowship at Utrecht University, then joined the faculty at UCLA, where she became associate professor with tenure before moving to her current position. Professor Cook's current research is on mathematical modeling and prediction of properties of complex fluids, especially highly entangled fluids such as worm-like micelles, and her mathematical interests are in modeling, nonlinear partial differential equations, asymptotics and perturbations, and her earlier work was in transonic aerodynamics. So Professor Cook received numerous awards and holds various positions, including being currently the president of the Society of Industrial and Applied Mathematics, known by some more often as SIAM, and Associate Dean of Engineering. She's former Editor-in-Chief also of the SIAM Applied Math Journal, a member of the Scientific Advisory Board of the Field Institute for Research in Mathematics. So her presentation today will be on non-Newtonian fluids and the mathematics of surfactant fluids. And so without further ado, please join me in thanking our guest today, Professor Cook.
Thank you. Oh, geez. I'm not sure I'm going to do this. So thank you very much. Just very nice of you to introduce me like that, but it just tells you how old I am, that's all. Somebody asked me today how I thought you should get in different fields, and I said, just keep going. If you just keep going, you'll get there. So the talk today is mainly for graduate students. So there are some people in the audience who are more expert at what I want to talk about than I am, but at least I'll give you an introduction. So the first thing I want to mention is Lydia mentioned that I'm president of SIAM, which is really great. It's an honor. If you don't belong to SIAM, you should. If you're a student, the membership is free. So try it, and then you can stay or not stay. It's up to you. And the national meeting this year is, guess where? Right here in Boston. So it would be really useful to join now and go to the meeting and see. It's industrial and applied math. There are lots of engineers, computer scientists, biologists, as well as mathematicians. So it's a great organization. It has now 21 SIAGs, was 20. SIAGs are SIAM interest groups. They have their own meetings, and they keep you up to date on certain areas. For example, there's one in applied PDEs, one in computer science and engineering, which is really successful. It may take over SIAM. Material science, mathematics of planet Earth, uncertainty quantification, so there's some really great SIAGs, as well as journals. So I just have to put that plug in as president, I have to do it, right? But it's great. Okay, so I'm going to talk about non-Newtonian fluids and the mathematics of surfactant fluids. It's very funny to talk about what something isn't, right? What's a non-Newtonian fluid, so we better do better than just say what it isn't. So what is a Newtonian fluid? I think all of you know what a Newtonian fluid is. It's water, basically. The equations tell you that the stress is proportional to the shear rate. That is, the viscosity is constant. And some examples are water, honey, molasses. They may have very different viscosities, but the viscosity is constant. OK, so what else can happen? Well, on the left here, you can see that the viscosity is plotted as a function of velocity or shear rate, depending whether you're stirring something. So if you're stirring water, you have to work as hard as you want it to go fast, so linearly. But if it's, and the viscosity of water is 10 to the minus 3 Pascal seconds. For honey, it's 1. And for a surfactant solution, it changes, but at 0 shear rate, it's all the way up to 14. So that's an example of how useful some of these surfactant solutions are, as they have very high viscosity. You can see in the picture that maybe this is going to work, maybe it isn't. There it is. Here is a constant viscosity, so water is here, molasses is here. And here we have something shear thickening. That means the viscosity increases. And here we have something shear thickening. I think everybody knows what oobleck is? Yes? No? Yes. OK, so you've all seen the YouTube of people running across the swimming pool. So that's shear thickening. It just could be cornstarch and water. So if you do something to it really quickly, it's like a solid. If you do it more slowly, you'll fall into it. It's like a fluid. But there are other things like shampoo that are shear thinning. And that means that as you shear it, it actually gets easier to shear, right? So when you pour the shampoo, it sits in a little ball in your hand. If it's good shampoo, if it's not, it just falls through. But if it's good, it sits there. And then when you decide to rub it, it actually thins. So non-Newtonian could be something that shear thickens or shear thins. But it could also be something, it also has often elasticity. So this is a wonderful YouTube. Well, I don't have the reference for the YouTube. But there is a beaker of clear fluid, looks like water. And he takes it and he pours it. And then he says, oh, I didn't mean to pour it. And it all goes right back in the beaker. And then he takes the beaker again and he pours it and takes some scissors and cuts it. And it doesn't splash. And what he has cut, above what the cut, just goes back in, right? So this is an elastic recoil. It looks like a fluid. It acts like a fluid. But it also has elasticity and tries to stick together. So most of what I'm going to talk about is going to be viscoelastic. So it will be shear thinning or shear thickening and have elasticity. So here are some examples of why something might be non-Newtonian. So on the left, you see that these are, the scale is 100 nanometers. And you see that these are very long fibers or something that's entangled. The middle one is a surfactant. That's what I'm going to talk about mostly. The one on the right is filamentous protein, effactin. And the one far on the right is actually a colloid. It's more like it's what's in milk or yogurt. So you can see that they all make patterns. You find non-Newtonian fluids everywhere, right? Mucus is a non-Newtonian fluid. Asphalt is a non-Newtonian fluid. Plastic, right? When it's in liquid form, before they make a fiber or a pail, it's long chain polymers that get entangled. It's non-Newtonian. Fracturing agents to enhance oil well extraction sometimes are non-Newtonian. They're often polymer or surfactant. Detergents, shampoos, and most foods. Nobody likes ketchup that just kind of flows out. You like it to be nice and kind of thick and stick where it should be. So you want additives in the foods so that they behave nicely. So there are non-Newtonian fluids all around. So what do you do with a non-Newtonian fluid? It's very complicated. These fibers will affect the flow, and the flow affects these microfibers or the microstructure. And so what rheologists do is try to study it in very simple flows. So there are two sort of very simple flows, and the one I'll talk about today is shear, just because it's easier, and I only have an hour. I don't think you want to stay for 3 hours. But the other one that's interesting is extensional flow. So in shear flow, you're thinking of two planes, and the bottom one's fixed. The top one, you might move at a constant velocity. You might just move it back and forth, or you might move it and stop and try to see what's happening to the fluid between the two, right? And ideally, the simplicity of a shearing flow is that the velocity then is only in the x direction, so there's only one component of velocity. It only changes across in the y direction, and so that the velocity vector becomes just a single scalar. The shear rate tensor only has one. It has two components, but one, they're equal. So that makes that much simpler. And then you want to try to understand, given a velocity, what happens. And you need a constitutive equation to tell you what kind of fluid you have. So the constitutive equation tells you the force or the stress as a function of maybe the shear rate, the strain, maybe time, and that really tells you what the fluid is. So part of what we want to do is understand the constitutive equations for these viscoelastic fluids. And of course, nobody can get to infinite planes, right? So how do we really do that? You do it with many different ways, but the way we'll talk about it is with Taylor-Coët cell. So you have two concentric cylinders. And when we talk about them, the outer one will be fixed, the inner one will rotate. And if the radius is very large and the gap size is very small, it's almost planar flow. Not quite, but almost. OK, so if you were doing this macro scale, you would want to know a constitutive equation that would tell you what the material was. You'd have to worry about conservation of momentum and conservation of mass. Conservation of mass, as long as we're doing shear flow, we don't need to worry about. It's automatically satisfied, which is why this is a nice flow to do. Extension is much more interesting. Extensional flow is when you pull things apart, but we're not doing that today. OK, so we need a constitutive equation. And people have all kinds of ideas for that. So the first one is the Newtonian constitutive equation. The stress is proportional to the shear rate. That doesn't work if it's non-Newtonian. So people try generalized Newtonian fluid constitutive equations. And these are just kind of made up. They may let the viscosity be power law. So you can certainly get shear thickening and shear thinning, depending on the coefficients. Of course, if you just do a straight power law, things will blow up at zero shear rate. So they get it fixed up by using this Karogia-Suda model, which basically fixes it at zero shear rate. But these are just empirical, right? And they don't tell you anything about elasticity. So how can we do better than this? One way is to think about spring in a damper. Everybody knows that. You've done that in ODEs back in who knows where, right? And that's obviously viscoelastic. It's got a viscous damper, and it's got an elastic spring. And if they're in series, if you want to find the displacement, you add the displacement in the spring to the displacement in the damper, and that will give you what we call the Maxwell model, right? Which is just lambda d tau dt plus tau is minus eta naught gamma dot. OK, that's a nice linear possible constitutive equation. Right now, we're all just doing one dimension. And one thing I wanted to do with that constitutive equation, we can solve it, right? It's constant coefficient. Everybody can easily solve it. And you've done this probably before, but you may not. You've always thought that's just some kernel or impulse function or Green's function or something they told you about in math. But actually, if you think about it, this is a fading memory. So it says, as opposed to the generalized Newtonian models, where if you knew the shear rate right now, you knew the stress, here you need to know the history, right? And that's part of the elastic thing. OK, and that's also typical of, let's say, silly putty or oobleck. If you do something suddenly to it, it behaves like a solid. If you do it more slowly, it behaves like a fluid. And it has some memory. It takes a while to change. The other thing I wanted to mention about this is that the step strain, so if we just moved the cylinder and then stopped, it would relax like e to the minus t over lambda. So we'll come back to that later, but it's always an exponential relaxation. OK. You can also solve this in the small amplitude oscillatory shear. So I said, what if we take the inner cylinder and we just move it back and forth, back and forth? So that means the strain is gamma naught sine omega t. It's easy. Again, constant coefficients, easy to solve, undetermined coefficients. And the solution comes out with an in phase with the strain part and an out of phase, right? So this part would be the viscous part. This would be the elastic part, stress proportional to the strain, stress proportional to the strain rate. Here are the coefficients, G prime and G double prime. And you notice that for small omega, this one wins, right? Omega lambda is much bigger than omega squared lambda squared for small omega lambda. And for large omega lambda, this goes to 0, and this goes to 1, or G naught. So this purple one is the loss modulus, or the part that's the viscous I'm going to call it fluid, but it's not right now. It's just a mass spring. And this is the elastic part. Where they cross is where you change over from a viscous to a solid, elastic solid. And so we call that, the inverse of that, the relaxation time. They're equal when omega lambda is 1. And so that gives us the relaxation time. So that tells you if you're doing something at a very low frequency, very slowly, behaves like a fluid. If you do it very quickly, it behaves like a solid, right? So this is a fairly decent model. So why would we want to use it, or what kind of viscoelastic fluid do I want to talk about? So I want to talk about worm-like micellar solutions. So surfactant molecules are amphiphilic. They have a hydrophobic tail and a hydrophilic head. That means that when you put them in water, they want to hide their tails. And so they may form a sphere with their tails in the middle. But then depending on the concentration and the salt, the cylinder might actually become more of an ellipsoid. And eventually it turns into a very, very long, floppy worm, right? So here is, oops, sorry. So here are the heads out, and the tails are all being hidden inside. And this is an example of what's happening. So they are all getting entangled. They're very long and floppy, and they entangle just like polymers. But the difference is they break and reform. They just keep breaking and reforming, breaking and reforming. And so they have an extra way to relax. It's not just that if you do something suddenly, they can't relax, and slowly they can, but on top of that, they keep breaking and reforming. You can see some of this is a, whoops, wrong button. This is you can see them here, and again here, this is 100 nanometers. It's about the same size, so they are up to a micron long themselves. And there are many different kinds of surfactants, and they're called living in polymers because they break and reform, and if you rip it apart and put it back, they can reform. So, okay, so these long worms can affect what's happening. If you think of maybe hair in the sink drain, right? One hair doesn't matter, but if a whole lot get there, they mat together and they can clog the whole drain. So that's what happens. Okay, so another way to think of it is, I like cooked spaghetti. That was the poster, so I have to mention it. If you have a dish of cooked spaghetti and I want to give you a little bit, so I try to just take a little bit, I can't, right? The whole plate comes up when I try to take 2 forks. So it's like a solid on the short time scale, but by the time I get it to your plate, there's nothing left, because why? All the spaghetti strands have snaked out, right, of the entanglement. That's called reptation, and that happens also. Now imagine that they could break at any time and reform, right? Be a big mess. So that's what happens. And typically, worm-like micellar solutions are used in detergents, as I said, and also in oil well enhancement, fracturing fluids. Okay, so let me tell you some properties of worm-like micellar solutions, why they're interesting. So if you had a constant velocity of this inner cylinder and the outer one's fixed, you would expect to have a linear velocity profile across the gap, right? 0 at the outer cylinder, v at the inner cylinder, and linear across. That would be what happens if it was Newtonian. Okay, this is what happens for fairly small velocities. What happens as I increase the velocity of the inner cylinder, it suddenly shear bands. So you get a very high shear rate near the inner cylinder and basically nothing happening near the outer cylinder. And as you increase the velocity further, the intersection here moves towards the right, and eventually everything becomes a high shear rate band. But it means that if you think you know what's going on inside, you don't, right? Because things are moving very quickly here, and almost nothing's moving out here. At the same time that happens, if you look at the shear rate as a function, stress as a function of shear rate, if it were Newtonian, the stress is proportional to the shear rate, right? So it should be linear. So here it behaves as if it's linear. but exactly at the point where the shear banding starts. The other thing is that you could force it through a pipe with a pressure, like turn on your hose. And if you do that, you also get a shear flow. And what happens is it starts with a parabolic profile, which is what you would get for a Newtonian fluid. And as you increase the pressure, you get shear bands at the wall. So now they're at the wall, and you get an almost plug-like flow, almost constant, the rest of it. And what happens when this is just suddenly the fluid can get pushed through, right? So here I have the volumetric flow rate plotted as a function of the pressure. And it starts out like water. It's just slowly increase the pressure, you increase the volumetric flow rate, and then suddenly it spurts out, and you have a very much increased volumetric flow rate. So that's something you really need to know if you're processing something or filling shampoo bottles. It's going to have a big effect, right? You're going to have to close down the whole assembly line. OK. So how could we model this and what's going on? And we have enough background now that I think we're ready to do it. So here's one more thing about these worm-like micellar solutions. If you do small amplitude oscillatory shear, so you move the inner cylinder back and forth, and we just did this with the simple Maxwell model. But now here we have some experiments, and you can see that it looks like, let's pick, these are very different preparations, but let's pick the circles. So this is the storage modulus, and the corresponding loss modulus is this. So it goes up and down like it would for a Maxwell model, but then instead of continuing down, it goes back up again. Right? And actually, the suspicion is that this goes up again, too. So it's not like a single Maxwell model, right? But maybe it's like two, a sum of two, that are very, very far apart, because this is not going to, this crossing is about at 1. So the relaxation time for this Maxwell mode would be 1 over 1. But the crossing time for the next mode is probably going to be way up here. And so the relaxation time is going to be 1 over 1,000, or something like that, right? So this is why actually worm-like micellar solutions are much simpler than polymer solutions, because polymer solutions will have many modes. And here we only have 2 modes, probably, and they're very separated. So if you're going to model them, it would be interesting to use just 2 sort of Maxwell models, but with very different relaxation times. And that's so. There are many, many models of transient networks. And I should say now that that's what's happening with these worm-like micellar solutions, because they get entangled, they can untangle, so they're not permanent networks, right? And they can also break and reform. So of the many models, this is more of a, This is more of a model for spaghetti. This says that it's so entangled that the spaghetti can't move except in a little tube along itself, because it can't move sideways at all. This is called the reptation model. This is a slip link model. The one we're going to talk about is more like this. It's sort of beads and springs. So, OK, so let's talk about elastic dumbbell theory. After all, we did a nice series, spring and damper. So we might as well use everything we know. So we're going to talk about dumbbells. So it's going to be a Hookean spring. Of course, it'd be better to do something nonlinear, but let's start with that. And dumbbells in a fluid, and there will be drag between the beads and the fluid. And so we'll just have a pipe full of these dumbbells and see what happens if we try to model those. So here's the dumbbell. And I apologize, I should have changed the notation. These big R1 and big R2 are the same as little r1 and little r2. So we can locate each bead, and we can locate the center of mass. And we can also figure out how much the spring is stretched, right, which is going to be Q. And if I wanted to write down an equation to tell me what's happening here, that's easy. The position of the bead at time t plus delta t is its position now. And then we have to put all the forces on it. So we have convection because the fluid is moving. We have a spring, and this delta Ri is really the Q. And then we have a stochastic increment, right? So we could actually sit down and just put a whole lot of dumbbells in there and watch where they're all going. I could also, instead of considering these as the unknowns, I could subtract these and try to get a mean field theory just for the connector vectors, right? So Q is R1 minus R2 for each bead spring dumbbell. Now I've lost the details of the network, but the advantage here, this is the probability that I'll find a dumbbell with a connector of Q at time t, perhaps at a position R. And so this is just a conservation equation. Q is now a independent variable. Before it was a dependent variable. And this is just the convection. I lose dumbbells of connector Q because of convection by the fluid. They get lengthened because of Brownian motion or because the spring pulls them back. But I've lost a lot of detail here. It also turns out that if I multiply this by QQ, so this is tensor, and integrate it over all possible connectors, it basically gives me the stress. And that's because I have a Hookean spring, so that's this Q, and this Q comes from the volume. If I have a face, I have to figure out what's the volume that I have to look at that all of the connectors with that Q could be in. So that makes it very simple. If you had a nonlinear spring, it would be more difficult. So because this is a nice linear equation, and because the stress is just the second moment of C, it turns out that for this model, I can integrate it up and I can get the stress as a nice PDE. Or if I'd like to do the stress, take out the identity so that I have the stress as 0 in equilibrium, it's this equation. And this should just look to you like the Maxwell equation again, right? Except that it's a tensor equation. And before we had a scalar equation. And the other difference is that I have a convected derivative because now I'm not doing x as a dependent variable, it's an independent variable. So this is a quasi-linear equation. It's very nice PDE, and you can try to solve that equation. You can solve it in shear easily, right? And certainly in linear theory, it just becomes our old equation because in linear theory, all these terms drop out, and I'm just back to d tau dt. So small amplitude oscillatory shear is going to be the same thing. Okay, so that was a bucket of dumbbells moving down the river. But now there's another theory called transient network theory, which says that, well, let's just look at the mean field. Let's look at the probability of finding a dumbbell of extension Q at time t. Let's assume that it's only affinely convected. And we could break it, and we can reform it. And this is more in line with what the micelles are doing, right? So we break them and reform them. We can actually put them together and have both. And this would be a network of elastically connected chains, right? So here's the elastic part for the connection, and here's the creation and destruction, which we talked about for worm-like micelles. Of course, the trick is what is C and what is D, right? And that's a problem. And the other problem is if we want to integrate this up to the macro scale, so if we're going to multiply by QQ, get the second moment and integrate, it really matters what is C and what is D, because we may not be able to do the integration, right? So we may not be able to get the macro scale equation. It was very simple with a straight Maxwell model. Now it's a little more complicated. All right, so here is a model that we came up with for understanding these worm-like micellar solutions. I don't expect you to take it all in. I just want to point out a couple things. First of all, if the right-hand sides are all 0, it's very simple, right? Because this is just a Maxwell equation. This is another Maxwell equation, right? So we've just added 2 separate modes, upper convected Maxwell, and very different relaxation times. So epsilon is very small. So this sort of came out of the SAOS. It says we have maybe 2 lengths. Maybe somehow this behaves like 2 lengths. We'll call them the A's are long, the B's are short. The A's can break into 2 B's, and the B's can be combined into an A. Of course, it's not that simple with the worm-like micelles, but the way the small amplitude oscillatory shear looked, it suggested this might be true, right? Now, what do we have on the right-hand side? Well, here we have the breaking of the A's, and here we have the creation of A's from B's, and then the equivalent here to keep track of everything being the same. And I think maybe the 2's, yeah, okay. And we will also, therefore, have to have equations to govern A and B, because those are going to change. The numbers of A's and number of B's, depending how they break. And this part, we don't need to talk about right now, but this is also interesting. Okay, so that's a sort of messy equation, because if you look at it, how many unknowns? B is a tensor, should have 9 unknowns. In fact, because we're in shear, it only has 4. A is a tensor, it also has 4 unknowns. NA and NB are unknown. And since we know that we might get an inhomogeneous flow, we can't assume gamma dot is constant, because we saw the shear banding pictures. So we have to couple this also with conservation of momentum, right? So it's a big system, nonlinear reaction diffusion equations. What is CA and what is CB? That's interesting, because I'm already at the macro scale. We chose CB to be constant. We chose CA to be this nonlinear function. I'm not going to go into why it's there, but you can see that we did it after at the macro scale, and the breakage shouldn't depend on averages over the whole system. So it works. We were very lucky. There's reasons we chose this, but I'll come back to that later. Okay, so we have the system of nonlinear reaction diffusion equations, and we have to put initial conditions. We have to put boundary conditions. It's a fading memory, so it cares how you start it. So you have to ramp up the cylinder, and depending how fast you ramp it and how much inertia is in the system, you get different solutions, which I'll explain in a minute. But in the end, that's what the solution looks like. So this is great, because here's shear banding, right? We got shear banding. This is velocity as a function of position across the gap. So as you increase the velocity, the intersection here moves across the gap. And at the same time this is happening, we get a plateau. So that's really great. It turns out that you can have multiple bands. You can have more than 2 shear bands, depending on how fast you ramp it and what the inertia is. And it's within a reasonable parameter range that there are actually experiments that show the shear. So as you start it up, what happens is a wave goes across the gap, and it reflects back from the other wall of the cylinder. And just as the shear bands are forming, it crashes into them and destroys that, and so that you get more than one shear band. Okay, so after we had this model and we did this, we thought we should look at the spatiotemporal results. And on the right, you can see what happened is I told you we have to ramp it up. So we ramped this up. We started it at 0 and ramped the velocity up to 6 and watched what happened across the gap. And first we saw a linear profile across the gap, like it was Newtonian. And then it realized, whoops, I don't like that. So there was some non-local effect here. It started to sag Then it sagged way down to here before it settled back to where it really liked to be with just the 2 shear bands. When we ramped it up differently with inertia, we didn't get this because it crashed before here and formed the multiple bands. But when we saw this, we thought, whoa, something's wrong here, right? How can you start this never moving? This is moving in this direction, and the fluid has a negative velocity, right? But then we found this really great experiment, and I'll see if I can get this to work. So this is an example which isn't worm-like micelles, but it's a preparation that's somewhat like that, so it's very long chains in a sea of short chains. When I show you the movie, and it's from Shichi Wang at Akron, the inner cylinder is the top, and it will move to the left, and the bottom is the outer cylinder, and he has it seated with these spheres, so you can see what the flow is doing, right? So let's watch what happens here. So it's moving sort of like a linear profile across the gap, and then whoops. Now it's settling down, and you can see that it's shear banded. It's basically not moving in this part, and this was moving very quickly. So that's exactly what it does. So that was kind of fun. Although later we realized that almost any constitutive curve that's non-monotone, that is, if you have a curve that the stress is a function of the shear rate, if you fix the shear rate, right? So don't worry about momentum. If you fix the shear rate and assume that's the same across the gap, if the stress, the flow curve, the stress as a function of shear rate is non-monotone, then almost any of these things happen. So it's not really particular to this model. What's great about this model is when we did it in extensional flow, we got also realistic results, which other models that are just the non-monotone curve didn't. OK, so that gives you an example of some way of modeling these. And I should also mention that in the high shear rate band here, of course, we have demixing. So here, we have very few of the long chains. They've all broken. Here, it's almost an equilibrium situation. So there's that. And also, probably in the real flow, they're also aligning. OK, so the trouble is, where did we get this breaking rate from? And is this right? And what is this telling us about the worms? What could we get from the mesoscale that we could integrate up to the macro scale? That's a problem. And in fact, it turns out that the properties of these worm-like micelles depend very much on temperature, on salt concentration, on concentration of the surfactant itself. And what I've shown you is just at one temperature, at one concentration. And if you change things, they're different. So for example, way back in 1991, there was an experiment done where they actually fit relaxation. Now remember, I told you the Maxwell model relaxation is e to the minus t over lambda. And even if I make the VCM model, the model with the 2 Maxwells that I showed you, if you do linear theory, it's e to the minus t over lambda again, right? But here, he looked at what happens if you change the salt to surfactant ratio, and he found that he could fit the results to a stretched exponential, not an exponential. Alpha is 1 a lot of the time, so it is exponential quite a bit over a large range, but it changes here. So what on earth could we change in the model? How do we don't have a clear understanding of what parameters we change to get some behavior like that. And there on the bottom is his actual fit. And it's not just small t or large t. It's actually, because his lambda is 3.6, it's over a range of times. OK, so there are lots of experiments on soft materials, soft gels, where they don't get exponential relaxation. So You gave something a strain and watch what happens. And we said for Maxwell, it's e to the minus t over lambda. We just said that for changing concentrations, it's e to the minus t over lambda to the alpha. Sometimes people get things that are actually power law. So you will find in the literature that they fit their experiments to this or to this, which are again empirical laws. Actually, I'm amazed in the asphalt literature because that's what they do. And really, you're just fitting to, a stretch exponential, or you're fitting to a power law, and you don't understand why it's happening. So there are people have noticed that there's something called a fractional derivative. I'm not going to take time to go into it, but it's a natural extension of a regular derivative. It reduces to a regular derivative if the parameter alpha is an integer. But actually, the solution, well, so people have said, OK, why don't we have, instead of a Maxwell model, a fractional Maxwell? And you can write down the solution to this, and it does have power law decay, right? But it doesn't really help us, again, because this is macro scale. And it's pretty hard to figure out how. There are ways you can get this from the mesoscale, but not if you have nonlinear forces, like we do. Not if you have maybe aging. And it's not even clear how to write the solution when it's in tensor, right? For scalar, OK. And there is a paper where they've written it for a tensor, but it's not even quite clear. So anyway, this really comes from what's called the continuous time random walk instead of Brownian motion, which actually says things are being caught and trapped. And so why don't we just go back and do the mesoscale simulation itself? Why should we be working at the macro scale, right? We can do things at the mesoscale, add them up, and get the macro scale result, but we don't need to add them up and then solve the problem. So where we're going with this now is we are trying to look at it as a transient stochastic network, which is what it is. We will have connections. These are nodes that can connect different parts, and they're transient. So they die after a while, so the node releases. So there is that relaxation as well as the spring relaxation. And you saw this equation before. We just track each bead and each spring. And it's a bit difficult, but we track the topology so we know where everything is all the time. And we started this just with an F is 2. So that's just the breaking reforming, right? So there's no entanglements yet, although that will be the next step. And, yeah, OK. So this is following the beads, like a Maxwell model. But now we also add that they can break. The nodes break, and they can reform. So the dumbbells, if you want, can join or break apart. And again, this is probabilistic. And the question is, what is tau? Because tau is the mean lifetime of a node. And what is d, the Kepler radius? And this has been done in pieces by other authors before, but not completely. So we have to look at the energy of the connection and the disconnection. And that actually tells us the local mean lifetime as a function of the stretch, right? So if you have a node, and if the bead spring connected to it is really stretched out, it's going to pull it out even easier than just the normal breakage. And so when we do that, we can actually track what's going on and what is the length that we're generating. So this is the number of dumbbells in a chain, and this is the number density of that length. And you can see that as the lifetime, the mean lifetime of each node is big. So here tau is 10 in the blue, and it's 0.5 in the red, that we get a much broader distribution. It's very polydisperse. Whereas when it's the shorter time, we get the red, which is almost all short chains. And this is typical of worm-like micelles. So they have 2 times to relax, right? One is the breakage time, and one is the reptation time, the time for it to wiggle out of its entanglements. If the breakage time is much shorter than the reptation time, then basically the breakage dominates. And so that's why it's so simple when we just get 2 Maxwell modes. If the breakage time gets much longer and the reptation time wins, then it's more like spaghetti. And then we get something that's much more polydispersed. And the breakage really isn't count, right? So that's one of our first results of doing the full mesoscale modeling. And a particular interest is the viscosity at steady state. And if we just have a constant mean lifetime and a constant capture radius for each node, then you get something that's almost Newtonian, but it's got a little bit of shear thickening here. And this is because as the chains get longer, when they break, they have more chance to recombine because they go through a larger distance. They're longer, and as they get pulled back, they go past more people, more beads, nodes. If we include the fact that the lifetime of a node depends on the stretch of the chain, so the chain may be pulling it out itself, then we get shear thinning followed by thickening. And if we also decide that the radius of capture depends on the length of the chain, then we can actually almost get rid of the shear thickening. So there are a lot of results in here, and the real question is, can we get a better idea of what are the energies involved in the combination and in the capture and the breakage? And those will then depend on temperature, they'll depend on the salt, they'll depend on the concentration, and so we should be able to understand better what is the Maxwell scale result. So just to summarize, I first talked about homogeneous flow, right? So we had gamma dot constant. If it's Newtonian, for sure it's homogeneous flow. We talked about mesoscopic simulations as well as macroscopic simulations. I showed you that worm-like micelles have a region in which they have inhomogeneous flows. They shear band. And I mentioned you could actually have multiple shear bands depending on the ramp time and the inertial effect. So what's in the future? The future is do nonlinear springs. These were all Hookean springs, not very interesting actually, although there were a lot of interesting results. Non-Brownian motion, continuous time random walks. Understanding better what are the energy landscapes. So far it's just a parabolic potential well. And right now we only had the breakage recombination. We didn't really have the entanglements. So trying to understand what the entanglements are too. So I know that's a very probably mathematical talk and an overview, but I hope that it gave you some idea of how people do some polymer and worm-like micellar modeling. And if you want more, you should take a class, probably in mechanical engineering. It's really fun. Thank you.
Questions?
A non-mathematical question. If they're using these for fracking fluids, is the idea that they can inject a lot of fluid with very low energy and then it becomes viscous, so they pressurize it and they can fracture the rock without the liquid getting out of the way?
Yep. Yep. And then they can just wash it out, right? Right. Exactly.
Other questions?
The parameters to the Hookean spring in the damping model, the VCM model, are they obtained by fitting to data, or is there a way of obtaining them from a molecular perspective? Say we are given the structure of a surfactant and we know how it behaves and what is the length of a typical worm-like micelle. So then can we predict those parameters from a molecular scale perspective?
For the VCM model, a lot of the parameters were done by fitting to experiments, right? I mean, the epsilon, for example, you remember that I said there's a very small relaxation time for the short species. Sort of doesn't make sense. It's very small compared to the fact that we only have that they are half as long as the long species, right? So there's probably something else going there, and those were done by experimental fits, right?
You mentioned as future work integrating non-Brownian motion into that.
Sorry.
You mentioned as future work integrating like a continuous time random walk or non-Brownian motion. And would that just be through a fractional derivative, or how do you?
No.
incorporate that
I would
in the
do that
model?
instead of doing the Brownian motion in the in that equation. Yeah. So right now that's just a Wiener process. So I would do there.
Since it's up, could you say a little bit about how you would introduce non-Brownian or not? And if I want to generalize the Wiener process, I can change its statistics in space or in time. So you're thinking about just doing it in terms of time, right?
Yep.
So macroscopically, you can do an inhomogeneous spatial thing relatively easily. Do you think there's a hope of doing mesoscopic simulations that are also inhomogeneous in space and in time? So on the mesoscale, you'll have to track multiple network points within each, say, finite volume of a spatial discretization. If I wanted to capture a shear band in a non-Maxwellian
How am I going to do a shear band in this?
Yes.
Right. Okay, so right now what we've done is just one little box. So eventually we'd have to do some parallel computing and put the boxes on top of each other. Right now we just assumed a constant gamma dot for these. And they're some homogeneous. So certainly we're going to have to do a whole lot of boxes. And of course you also have things disappearing from the box. So you have to use Lees-Edward boundary conditions to put them back in. So that's how we would get to the inhomogeneous. So each little box would be homogeneous, but then we would be connecting them at their boundaries. Right. Right. Big problem.
Other questions? I have one. So in your modeling, in the modeling of the breakage and reformation, you have a term of breakage that is proportional to the total number, so the n, and then the reformation is not. And so what is that assuming in terms of the, for the C coefficient that you had in that equation?
You mean in the VCM model or in the?
In the one that included breakage and reformation in the network.
You mean this? Or you mean
Previous.
Oh, you mean way back in the simple this?
Yeah.
Oh yeah, I haven't. That's a good question, right? So in the VCM model, the reforming we took to be a constant times the number of short chains, right? So here, the reforming is this. So, and CB was taken constant, and you need two Bs, so it was a very simple model. In the mesoscale model, the reforming is just whenever two get within a certain distance of each other. And that needs to be fixed. I mean, that's a critical problem, yeah.
Okay, so you're now including the concentration that is influencing that mean distance between them.
The concentration
for the phi. So the phi is the density population, and so you have a breakage that is proportional to phi, but then the reformation rate basically is fixed and does not depend on the overall population into that fluid.
Well, it does
vicinity.
only in the sense that if you have more, then there's more chance there's going to be one close to the.
Exactly. So then
the
you're just
node.
basically increasing C depending on the concentration in that fluid and changing.
Well, it automatically, I mean, if you had a fixed C and you increase the concentration, there's more chances that they're going to meet, right? So it does change it. So the concentration, when we're doing these, I think you mean when we're doing the mesoscale simulations, I think I showed, Yeah, so the number of nodes, and here's the number of nodes. So if I decrease that to 1,000, it's essentially changing the concentration. There's less chance they can meet up. So I'm getting a very different result here. Yeah, that's the black as opposed to the red. But I can also change the number of, so that's the number of nodes. I can also change the number of dumbbells in the box, and I get a very different result. So it depends. The concentration in the box gives me that automatically, right?
Other questions? No? Okay, so thank you very much.
Thank you.